Hello there. Today in our science class, we are going to look at a new topic about particles in solids, liquids, and gaseous state. In our previous lessons, we defined a term matter as anything that occupies space and has mass. And we all realize that all materials we have here on the earth are made up of small particles. These materials are also what we refer as matter. So therefore it tells us that all matter is made up of very small particles within it. We also realize that matter, which has the small particles, can be placed in various states. And the various states are the solid state, liquid state, and gaseous state. To understand matter, we require some ideas, and the ideas are matter or materials that have the small particles have the matter in it, the small particles in it being in constant motion. We also need to understand that the small particles in matter are always held together, but the forces holding together the small particles vary in strength. This helps us to understand that as much as we know we have particles in solid state, in the liquid state, and the gaseous state, there are more. There's much information that underlies the states of matter. To understand the matter and the states, a theory was developed which will help us understand what is it when we say a solid, or what is it when we say a liquid, or what is it when we say a gas. The theory is given in two names which just mean the same, and that is a kinetic theory of matter, or it can also be called particulate theory of matter. Why kinetic theory of matter? It is to look at the energy in the particles contained in either the solids, liquid, or gases. Or why particulate is because you are looking at the small particles in the three states of matter. For this theory to be understood, that is the kinetic theory of matter, we need to look at a diagrammatic representation of the three states of matter, which can be as follows. Starting with the solids, let's use a rectangular box to represent the solid, and inside the rectangular block we have the small particles. Now, looking at this diagram, we are looking at the behavior, the description of solids. In a solid, the small particles, going by the ideas we have just given, we said that the particles should be small. That's idea number one. The particles should be very small, and indeed they are very small that your eye and mine cannot be able to realize it. But its effect will always be felt by you seeing a solid object. The other idea was the small particles are in constant motion. However, when you are looking at a solid, the small particles being closely packed, they are unable to move. Then what do? They vibrate in fixed position. Just like you, where you are seated or standing, you can vibrate in a fixed position. You are not moving, but you are vibrating. Then that is the character of small particles in a solid state. They are closely packed. Instead of moving, they vibrate in a fixed position. The other state of matter is liquid. Using the same rectangular box, we shall have our small particles in it. You now realize in this box, the small particles are close together, but not as much as in a solid state. You can see some small spaces between the particles. This makes these small particles to have one other ability that the small particles in solid state do not have, and that is they move around. They are mobile. They are free to move. This gives the liquid its property that is different from solids, its behavior that is different from solids, and that is the particles move around. This helps liquids to even move around. When you pour water in that glass of water of yours, you will find that it takes the shape of the glass. You pour it on a surface, it will flow because the particles are able to move around, and as they move around, they will always take the shape of the container they are being held in. This also shows that the forces attracting the particles in a liquid are lesser compared to the forces holding the particles in a solid state. And that's why the particles are loosely held, making them able to move around, free to move. The third state of matter is gas. Using the same rectangular box, you can see the particles are far apart. The particles in gas state are far apart. As small as they are, just like in liquid and solid, the particles are having very, very small forces of attraction between the particles. This makes the particles to be very free and have a higher energy of moving around the container into which they are being held. This explains the difference between a gas and a liquid. As much as the liquid, we said that the particles are free to move. They can roll over each other. But in gases, they are loosely held because of the very little energy, very little force that is in between the particles. This makes the particles to move and cover every part possible for the gas particle to reach. For the liquid, it will only occupy up to the level where the liquid can reach. But for the gas, they will always move to all parts of the container where the gas is being held. This is hidden in the forces attracting the particles. In the liquids, the force is a little bit stronger, but in the gases, the force is very weak. So being very weak, then it allows the particles to move as far apart as possible. The other thing we realize in the gas state is as these gaseous particles move around, they will start hitting on the wall of the container holding the gas. By doing so, it creates a pressure outside the container, what we call gas pressure. This is seen like in a case where you have a football. After air has been pumped in, that's a gas. So because of the particles hitting on the tube, the leather, then it makes the football to inflate, making it hard, and that is pressure. That shows the difference between a gas, a liquid, and a solid. They all have small particles. They all have forces holding the particles together, but the strength of the forces vary. Solids have the highest force of attraction holding the particles together, followed by the liquid, and the gases have the least force attracting the particles, holding the particles. They also have the particles being in constant mobile motion. However, we said for the solids, they are not really in mobile motion, but they vibrate in a fixed position. For liquids, they are mobile, and that's why the liquid will always roll over each other. The liquid particles will roll over each other to make sure they occupy all the space which follows the shape of the container, and the gases being far apart from each other, very free to move, they will always occupy the whole space into which they are being held. Now we have just looked at the diagrammatic representation of the solids, liquids, and gases. We have also looked at the ideas that we need to know so as to understand what are liquids, what are solids, and what are gases. Let's go through an exercise that will help us get a much more insight of what we have just discussed about particles of matter. There are two forms of questions. One will be a sentence whereby you are required to fill in key words. And the second one will be a general way of explaining what happens to various states of matter that are either in a solid moving to liquid, or a liquid moving to gas, or a gas moving to liquid, and liquid moving to solids. You understand that those are common behaviors of matter that we always experience in our daily life. So let's look at the first question. Here you are going to complete the sentence. So there's a keyword I will expect you to get just one word that you will have to place here that will have to agree with the statement we are having here and also agree with the following words. Another keyword here. I will give this one as an example, show you what you will do to the preceding one. Particles in solids are held dash by strong dash. Particles in solids are held tightly by strong forces. You remember in the diagram, the particles were close together. Why? Because they were held tightly by something. What is that something? The something is a force. So they are held tightly by that force. So the second one, they cannot move dash but dash in position. They cannot move dash but dash in position. Looking at our previous diagram, that is the diagram of the solids, we also saw that those particles do not move but they vibrate. So the statement here is asking us to look at they cannot move. Liquids, particles were moving. Gases, particles were moving. So it's only in a solid that we said they don't move, but they do a function that makes them behave like other particles when we're describing the particles in solid, liquids, and gases, and that is solids. They cannot move but vibrate. That's the statement. Not move but vibrate in fixed positions. The third one, C, is in liquids the dash. Now in liquids, as you look at this statement, please you go back to the diagram, because it is in the diagram that we are all going to understand what happens with the keywords. So from the diagram in the liquids, looking at the diagram in the liquids, look at the particles. How far are they or how close are they? So in the liquids, dash are dash together. In the liquids, dash. What are in the liquids? The particles. Just like in the solids, just like in the gases, so in the liquids, the particles are dash held together. In the liquids, particles are held together. But dash as tightly as particles in dash. So we have in the liquids, the dash, that is the particles, are dash held together, but looking at the particles in solids and in liquids, the only difference we said was In the solids, the particles are tightly held together, and in liquids, the particles are not tightly held together. So filling up here is but together, but not as tightly, not in comparison to solids, not as tightly as particles in dash, and that is in solid state. This question is comparing the behavior of liquids and solids in terms of the forces that hold the particles together. We can see that in the liquids, the particles are held together, but not as tightly as particles in solids. The fourth question, which is the last question, that is D. In gases. So these are questions that is going to look at the third state of matter, which is gases. So in gases, particles are dash So the fourth question here is talking about gases. And in gases, we said the particles are far apart from each other. Looking at the question, in gases, particles are dash held together. So particles are not held together strongly. Not because of the properties as we saw for the gases. So in gases, particles are not held together strongly and are. We said particles in gases, they will always move to make sure that all the spaces being held by the gas are filled up. So, and are free to move in any direction. So filling in is, in gases, particles are not held together strongly and are free to move in any direction. So moving to any direction is what makes gases to fill the whole container under which or into which the gas has been kept. The second format of the questions, this was the first format where we are just filling in the keywords. The second format is going to look at an explanation to some of the behaviors we see solids or liquids or gases in our daily lives exhibit. So second part of our questions is explanation, as I've said. So question number 1 is what happens to solids when they break away from their fixed positions. What happens to solids when they break away from their fixed positions? Looking at our model diagram, we say that particles in solid state are held tightly together. This makes them not to be able to move but vibrate in a fixed position. So this question is asking, what will happen to these solids when they break away? That is, instead of vibrating in a fixed position, they are now allowed a different behavior. Because when they break, it means they will no longer vibrate in a fixed position, they will now be able to move. What will happen is the solid melts. This is a property we always see. You have bought an ice cream. It is something solid in state, but you leave it for some time, you find it is changing from solid to liquid. What is happening is the solid particles in that ice cream, in that ice cube, in that frozen material is breaking away. That is, they are not going to vibrate in a fixed position, but now the particles will be able to move around. Because of that, it takes the property, the behaviors of a liquid and not a solid. That change is what we call melting. So what will happen to this is melting will take place. The solid will change from solid to liquid. Second question. What happens to liquids during evaporation? What happens to liquids during evaporation? Remember, when you are talking about evaporation, this is a change of state. A liquid is a different state, and after evaporation, that liquid turns to vapor, which is a gas. So you are talking about two different states, a liquid and a gas. The transiting point of this is evaporation. So what exactly happens when a liquid changes to a gas? What happens is to do with the forces that holds the particles. We said that in a liquid, the forces holding the particles are strong, but not as strong as in the solids. But when you look at the gases, we say that they are very, very weak. The forces holding the particles in gases are very weak, and because of that, the particles in gases are free to move to all direction. So when a liquid is undergoing evaporation, the forces holding the particles in a liquid are broken, are weakened and broken, so that the particles can be free to move a little bit far away from each other. And by doing so, they escape, because the forces holding the particles together as a liquid have been broken. And being broken and free, now the particle is free to go away. And that's why gaseous particles, during evaporation, you will see vapor coming out of that container where you are heating the liquid. The forces have been broken. The particle is free to move to all direction. Just like the previous exercise we have seen, particles in gases are free to move to all direction. And all direction, one of the direction is escape from the container and go into the space. The third question is, what happens to gas particles when they slow down. This is now the opposite of the first two questions. Looking at the first and the second question, we were talking about going from solid, liquid, liquid to gas. Now we are moving from we are going to the opposite. What happens to a gas particle when it slows down? Here you are talking about the small particles in that gas state. Those particles are free to move because they have a lot of energy. But now you are slowing them down. When you slow them down, it becomes the opposite of what happens in question 2. Because in question 2, the liquids were gaining more energy from the heating so that evaporation can take place. More energy. So the gaseous particles were having more energy. And that's why they are in a gas state. But here, now the gas particles, which have more energy, are being forced to slow down. Meaning, energy is being reduced. What happens here is it goes back to the previous state, and that is the liquid state, a process we call condensation. Here, the gas particles only reduce on the amount of energy they are having, and when they reduce, their movement also is reduced and they go down. Because when you have the energy, you will be jumping up here and there. But when you have been reduced by the energy, you will go down. You might sit. You might lie down. You might be standing, yes, but just at that particular position, just like the particles in a liquid state. As much as they are moving, but they are moving at a slow pace because they have less energy, because the energy was reduced. Just like the question 3 is telling us. Gases, their energy has been reduced, so they are forced to slow down. And by slowing down, they change state into a liquid state, which has less energy. The fourth question is, what happens to liquid particles just before changing to solid? What happens to liquids or liquid particles just before changing to solid? Remember, we are also changing a state here. We are moving now from a liquid to a solid. We are looking at two states that have different amount of energy, different levels of movement of the small particles. In liquids, movement of the particles is higher, they can move. But the only movement in solids is vibration. And here we are changing a substance that has its particles able to move, able to roll over each other, to a state where the very particles will be unable to roll over each other but can only vibrate. What should happen here is reduce the amount of energy. Look at yourself in a state where you are seated on a seat, but because maybe you are not comfortable, you will be trying to move around so that you change yourself, get that proper position where you will be very much constant. But you reach a state where somebody comes and holds you very tightly, pushing you onto that chair. I'm sure you will not be able to move around. It is the same thing that is happening here. So when you are being held very strongly or being pushed by that somebody on that particular chair, it means you are being forced, you and the chair, to be held tightly together. You and the chair. You are being forced to be tightly held together. Because of that, you will not be able to move. What is happening here? The liquid is to change to solid. So reduce the amount of energy in the liquid particles. By reducing, they will be unable to move. And because of that, they will remain in one fixed position, making themselves turn into a solid. This point is what we call a freezing point, where liquids are being turned to solids. The energies in the liquid particles have been reduced. The mobility in the liquid particles has been reduced to a level of just vibration in a solid state. The last question in this category, that's question 5, is why does covering of a swimming pool you can cover the swimming pool with anything so long as it's covered. Stop evaporation of water. Why does covering of a swimming pool stop evaporation of water? You can even mutate this question to mean, you can use anything, even a sufuria that is having some water, but it's open. It will be different from a sufuria having water covered on top. Look at any open surface, a lake, a river, any point that has water open and any point that has water covered. Their behaviors will be different in terms of that water in that container evaporating. So here the question is asking, why does covering of a swimming pool stop evaporation of water? Or you can as well say it, why does covering of a swimming pool reduce evaporation of water? This is in terms of when you cover, you keep away the heat energy from the environment. The environment can be warm, which might be because of the heat from the sun or from any other source of energies that will be coming in. So by covering the swimming pool, it means you are cutting off the heat energy from the environment. By doing so, you stop any infusing of energy to the liquid particles that is in the water, because water is a liquid and it has particles, and those particles can acquire heat energy. That heat energy is being cut off by covering the swimming pool. So if the heat energy has been cut off, then it means the particles will not gain the heat energy, and by them not gaining the heat energy, they will continue moving at their normal pace, not faster as it could have been if heat energy could have been added in. So if the movement is the same, then it will not be possible for the particles to escape, because for evaporation to take place, the particle must gain more heat energy so that it breaks away from the other molecules, making the particle to move freely to all directions. And if you can remember the previous set of questions, we said that the particles break and move freely to all directions, and all direction, one of the direction was to the space, into the atmosphere. But here the particles cannot gain the energy because they have been covered, so they cannot break away, so that they can move freely and to all directions. A supporting question to the same, which is in the same idea of gases and liquids, that's under question 5, is looking at evaporation of water but in different containers. Evaporation of water in different containers. So how will which container in the same sense of evaporation, we are talking about a liquid, that's water, evaporating. And evaporation means moving from a liquid to a gas. From where? From the heat energy that is being taken in by the liquid, so that the particles can break away and move freely to all directions. But here now we have 3 different shapes. They have been exposed to heating, maybe from the sun or from any source of heat energy, but at equal level. Container 1, 2, and 3. Where will you see evaporation being faster and why? And the answer is, in 1, evaporation will be faster, and in 3, it will be the least. Reason being, this one has a wider surface at the top, whereby when the particle breaks free due to the heating, breaks free from the liquid due to the heating, it can easily be lost. By moving freely to all directions, it can easily be lost, so that it gives space for the other particle just below it to come and also be lost. But looking at number 3, which is the least, it has a very tiny point or a small point where the particles that have broken loose, that are moving away, can pass through. Because of that, it creates a little bit a higher pressure of the particles. Higher pressure of the particles on the water. You remember in the diagram for liquids, we said that particles are free to move to all directions, and in the process they press on the container holding the gas, creating what you call gas pressure. The same will be seen here. The particles that have already broken loose because of the heat energy moving from liquid to gas haven't been lost yet. Because of that, they will start pressing on the container, at the same time pressing on the liquid particles that haven't broken loose. By so doing, they make the particles that are still in the liquid state not to be able to break away. But here, once they break away, they have a wider space into which they will get lost. And once they get lost, they give room for the other particles to come by and get lost. We have been looking at solids in particles in solid, liquid, and gaseous state, where we saw that particles in those 3 states are always in continuous states of movement, apart from solids where we have vibration of the particles. But we need to see the evidence of the theory we used to explain that behavior of the solids, liquids, and gases. We have to understand, is it true that this theory is real, as we explained that particles are always in a continuous state of motion. So here we have to look at how it can be done, or what aspects can we put into consideration or use to understand the kinetic theory of matter. A scientist, a British scientist, called Brown worked on an experiment using pollen grains, where he discovered that pollen grains, when put in water, they were seen to be in a continuous motion, where he didn't really at first understand why, but later on he came to understand that the reason why the pollen grains in the water were in a continuous state of motion was because of the mobility of the particles in the water. Just as we saw that particles in a liquid state are always in continuous motion. So when they are moving around, they were moving around colliding with the pollen grains. So at the end, the pollen grains also appeared to be in motion. The same thing can be seen in so many ways, one of it being like if you are in an enclosure of a room, where in that room there is some openings where light can go through, and maybe it is stuffed with the smoke, or a container that is holding smoke and light can go through. You will always discover that through that beam of light from the top, particles will be moving in a zigzag motion in all directions as they sparkle. If it is smoke, then it will be the smoke particles that will be sparkling as they move around. Why? Because in that container or in that room there is air, and air is a gas. A gas has particles that are moving in all directions, colliding with each other. So as they move around, they collide with the smoke particles, making them also to move in the same motion in a zigzag manner. To understand this aspect in our daily life, looking at a solid state, let's look at a case of your shoe or a car tire. What makes a car tire make the vehicle to stop when you apply the brakes? What makes you stop when you want to stop when you are walking? This is to do with the friction. You cannot experience friction if the two surfaces that are in contact are not hard enough. Just like I cannot feel a friction as I'm moving my hand, because this is a hard surface, but where I'm moving my hand is not a hard surface. Go pass your hand through water. You will not feel that friction, because particles in water are in a mobile state. But look at a state where my hand, I can feel some pressure. Your shoe and the surface, you can feel the friction. That car tire and the road, you can feel the friction. Why? The particles in the tire, the particles in your shoe, the particles on the road, the particles in my hand are in solid state, they are in a fixed position. So wrapping onto each other is forcing the particle to move, and yet it doesn't have the energy to move. So it will resist, and that is what we call friction. That proves or gives us an evidence of the kinetic theory of matter, that particles in solid state are in a fixed state and can only vibrate. To confirm the same, maybe you have been in a position where a heavy vehicle has passed by on a road, and you hear vibration of the building or structures around vibrating, but you cannot see them. You will only hear maybe the sounds. That shows that particles on the ground where you are standing, particles in that building are in a solid state, but they can only vibrate, and that's why you feel the ground vibrating. That is the theory as stated under solid state. In a liquid state, we have particles in motion. How do we prove it? Take a situation whereby you have a liquid like ethanol and water. You have seen people maybe in an environment where you are taking something, or let me use water and juice. You want to take juice. You will not take it in that original concentration. You will have to add in water. Look at that juice, it's a liquid. Look at water, it's a liquid. When you pour water in that juice, at the end of it all, you will not see water, you will not see the juice, but you will see a dilute juice. What happened? What happened is the particles in the liquid were rolling over each other. Particles in water were also rolling over each other. As they roll, they were mixing. Using a diagram, I can show it. So I'm pouring this liquid. You can see the particles are a little bit close, but not touching each other like in solid. The particles are a little bit close, but not touching as in solid. Liquid, liquid. So this liquid A being poured into liquid B. This can be water, this can be juice. Because of these particles being free and able to roll over each other, and also these ones being able to roll over each other, they accommodate each other. So the small ones and the big ones have mixed into each other. This is what we call a liquid dissolving into another liquid. The particles rolled over each other. The particles rolled over each other. They reached an agreement of each allowing the other one to come into position. This shows that it is true in kinetic theory of matter, particles in liquid are in continuous motion, because without them being in motion, then this liquid could not have allowed this liquid to come and rearrange the particles so that they are all in agreement. And lastly, looking at a gas as an evidence of kinetic theory of matter, I'm sure maybe after you have listened to this lesson, you will be going to maybe your home or somewhere, and just before reaching maybe your house, you meet a very nice scent of a delicious food being prepared. How did you get it? And yet the food is being prepared in your kitchen, not at the doorstep, not around your house. What is happening is the food that is being prepared produced scent. That scent, being in gaseous state, it moved in all directions, and all directions means up to that point where you met the scent. That shows that particles in a gas state are always in a continuous state of motion, and they move to all directions where they can manage to reach, because the particles are loosely held because of very, very weak forces of attraction, not like liquids and not like solids. With this, it gives an evidence of kinetic theory of matter that states that matter is made up of small particles. That's one, as an idea. 2. The small particles in matter are in a continuous state of motion, and that these particles that are in a continuous state of matter are held by forces that vary from one state to another. The solid state having the highest force of attraction, and the gas state having the weakest force of attraction. As an assignment, you're to be able to explain the following. Let's look at this question, which is going to talk about kinetic theory of matter, particularly addressing the solids. And the question is, explain why solids cannot be compressed. Explain why solids cannot be compressed. Looking at solids, we said that the particles of the solids are closely packed. Particles are closely packed, no space around. And this makes the particles to vibrate at fixed positions. So when you compress a solid, you are forcing it to move to a space that is not there. And because the space is not there, then solids cannot be compressed. So here, solids cannot be compressed because particles in solids are closely packed and have no room for movement. That marks the end of our lesson today. Thank you.